Welcome to Mastering Solutions. So for part A, we have to explain why the laser can't be perfectly parallel with no spreading, and that's because in the question, it says that what a laser beam really is light wave that's diffracting out through the opening. And so if you think about diffraction, what we've learned is diffraction causes, because it's basically a circular aperture in this case, it causes diffraction, which is going to spread by definition. And so it can't be perfectly parallel because it is diffracting, but when we're looking at it really close, it looks for all intents and purposes to us like it's perfectly parallel because the angle of its spreading is so small. Now, when we go to B, we need to figure out the angle to the first minima called the divergence angle, and we need to figure out what that is. So in this case, for a circular aperture, we'll be using the equation, this is B, theta is equal to 1.22 times lambda over D. So 1.22, and our wavelength, they tell us, is 633 nanometers. And D, the opening, is 1 millimeter. So we have 1 times 10 to the negative 3 meters. All right, so when we plug this into our calculator, we get 1.22 times 633 nanometers, and then that gets divided by 1 millimeter, which is 1 times 10 to the negative 3. All right, so we have 1, 2, 3, 4, so we'll say 7.7 times 10 to the negative 4, and what is that? This equation gives us radians. And now we need to convert that into degrees. So we can take 7.7 rads and we'll multiply that by 180. And we know in 180 degrees, there is pi radians. So the radians cancel. And so we have 7.7 times 10 to the negative 4. Multiply that by 180 over pi. And we get 0.044. So 0.044 is our answer in degrees for the angle up to the first minima of this laser. If we move on to C, we have to figure out the diameter in millimeters of the laser after it travels 3 meters. So L in this case, because that's the distance that we're traveling to, is going to be 3 meters. And the equation that we'll be using is 2.44 lambda L over D is equal to Y. And Y in this case is the distance from the central max out to the first minimum. And so the equation that we're going to be using for this is W is equal to 2.44 lambda L over D. We're using this one because we're trying to figure out the diameter at this distance. Well, that's exactly what W is. That's the diameter of the central max, or the laser beam in this case. And so it's set up for what we need. And so now we just have to plug everything in. 2.44 lambda, of course, 633 times 10 to the negative 9 meters. L we said was 3 meters. And the diameter, D we already said was 1 millimeter. So we have 2.44 times lambda, 633 nanometers, times L, which we said was 3 meters. And that all gets divided by 1 times 10 to the negative 3, 4 millimeters. Okay, and so we have 1, 2, 3. So we'll say 4.6. So we have 4.6 times 10 to the negative 3 meters, or 4.6 millimeters is the answer for part C, or the diameter of the laser beam at 3 meters. Okay, so finally we need to figure out the diameter after a kilometer. So we're going to do the exact same thing, only in this case the L is going to be 1 kilometer. And if we put that in standard units, that's 1 times 10 to the 3 meters. So exact same thing. So I'm not going to rewrite the equation. We're just using it right here. So we have 2.44 times lambda 633 times 10 to the negative 9 In this case, the L is going to be 1 times 10 to the 3 meters, and all that is over 1 times 10 to the negative 3 meters for the diameter of the opening. So now we can just steal this equation right here, and we're just going to change this 3 to 1 times 10 to the 3. So that gives us 1.5. And so the width of the laser beam at 1 kilometer is 1.5 meters. So you can see, like we figured out up at the top with part A, it is actually spreading as the distance increases. At 3 meters, it's a very tight laser beam still. Out at a kilometer though, it's spreading quite a bit to 1.5 meters in diameter.